Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the prompt. Begin writing. The paradigm shift initiated by Alan Guth's proposal of cosmic inflation represents a watershed moment in cosmological understanding. His 1979 work, The Inflationary Universe: A Possible Solution to the Horizon and Flatness Problems, introduced a bold hypothesis addressing fundamental inconsistencies within the standard Big Bang model. This essay embarks on a meticulous journey through Guth's seminal paper, analysing its core claims, evaluating the supporting arguments, and dissecting the proposed solutions to the horizon and flatness problems. The examination will encompass a section-by-section appraisal, offering a comprehensive assessment of the work's internal logic and its enduring impact on the field. Section 1: Introduction and Motivation for Inflationary Cosmology. Guth begins his paper by outlining the shortcomings of the conventional Big Bang theory. He highlights the horizon problem, which arises from the observed isotropy of the cosmic microwave background radiation. Regions of the universe separated by distances greater than the distance light could have travelled since the Big Bang exhibit remarkably similar temperatures, a phenomenon seemingly violating causality. The flatness problem, concerning the universe's present-day near-critical density, is also presented in detail. The standard model requires an extremely precise initial density at the Planck time to avoid a universe either rapidly collapsing or expanding to emptiness. Guth argues these issues suggest an incomplete or inaccurate description of the early universe, setting the stage for the introduction of an inflationary epoch. The introduction establishes inflation as a potential remedy to these cosmological puzzles, motivating the subsequent detailed analysis of the inflationary mechanism. He does this by suggesting that this new theory fits with evidence at least as well as the reigning paradigm. Section 2: The Horizon Problem and its Inflationary Resolution. Guth confronts directly the puzzle of the horizon problem. Elaborating on the concept of particle horizons and their limitations, he elucidates that, within the standard Big Bang model, regions now observed to be causally disconnected should exhibit vastly different properties. He then proposes that a period of accelerated expansion in the very early universe, specifically exponential expansion termed inflation, could effectively stretch a minuscule, causally connected region to encompass the entire observable universe. This process ensures that all regions within our present horizon were once in thermal equilibrium. Guth's claim rests on the mathematical formulation demonstrating how inflation exponentially increases the scale factor, drastically expanding the early universe relative to the Hubble radius. The resolution is predicated on the idea that observable space was an infinitesimally small region prior to inflation, and that, through inflation, its contents were spread evenly across the universe. This expansion explains the uniformity of the cosmic microwave background. Section 3: The Flatness Problem and Density. Parameter omega. The paper then shifts focus to the flatness problem, articulating the fine-tuning required in the initial density parameter, omega. Guth demonstrates, at even a slight deviation from an ideal flat universe at the start would result in a significantly curved universe today, contrary to observational evidence. He then offers inflation as a solution with significant expansion. Any initial curvature is effectively flattened, driving omega very close to unity. Guth mathematically shows that during inflation, the density evolves towards the critical density, resolving the need for precise initial conditions. The argument relies on the exponential expansion diluting the effects of any initial curvature, smoothing the universe like the surface of an inflating balloon. In Guth's explanation, the overall universe may still be curved, but the observable portion is so flat as to appear Euclidean. Section 4: A Scalar Field and the Equation of. Guth introduces the concept of a scalar field, often called the inflaton field, driving the period of exponential expansion. He posits that the potential energy of this field dominates the energy density of the universe during inflation, resulting in a negative pressure state. The equation of state, pressure equals negative density, drives the scale factor to increase exponentially with time. Guth's argument here hinges on the field's dynamics, specifically its slow-roll behavior where its potential energy slowly converts into kinetic energy. Under these conditions, the universe expands at an accelerating rate. The scalar field provides the physical mechanism to drive the inflationary epoch, a postulate that requires a specific potential energy function in the field theory. It can be easily shown that in this case, the rate of expansion approaches an approximation of what would be found with a cosmological Section 5. The graceful exit problem and phase transitions. Guth recognizes a critical challenge within his initial inflationary model, the graceful exit problem. Inflation has to end smoothly, transitioning to a radiation-dominated era. Guth had envisioned inflation ending through a first-order phase transition, where bubbles of the true vacuum nucleate and expand, eventually colliding and reheating the universe. However, he acknowledges this mechanism produces extreme inhomogeneities leading to unacceptable density fluctuations far exceeding observed limits. The difficulty lies in ensuring a widespread and rapid transition following the sustained inflationary period. Guth admits in the paper that this is an open problem at the time of publication. The necessity of a graceful exit underscores the complexity of reconciling inflation with the standard Big Bang theory. Section 6. Density, perturbations and structure formation. While the initial model encountered difficulties in exiting the inflationary epoch, the paper explores the gyration of density perturbations, the seeds of structure formation. Quantum fluctuations of the inflaton field during inflation are stretched to macroscopic scales, providing the initial inhomogeneities that grow into galaxies and cosmic structures. Guth explains that the amplitude of these perturbations depends on the energy scale of inflation and the shape of the inflaton potential. The paper acknowledges the need for a more refined understanding of the inflationary dynamics to accurately predict the spectrum of density perturbations. The production of density variations from quantum fluctuations constitutes a testable prediction of the inflationary scenario. A more robust mechanism would be required to solve the problems of Guth's initial model. Section 7. Further considerations and open questions. Guth concludes the paper by addressing remaining uncertainties and outlining avenues for future research. He acknowledges the lack of a complete theory for the inflaton field and its potential connection to particle physics. The exploration of alternative inflationary models and mechanisms for reheating the universe are deemed essential. Guth also highlights the importance of observational tests, such as precise measurements of the cosmic microwave background anisotropies, to validate or refute the inflationary paradigm. The open questions underscore the exploratory nature of the work, inviting further investigation and refinement of the inflationary hypothesis. The acknowledgement of these issues indicates honesty and scientific rigor. Section 8. Impact and initial reception of Guth's model. Guth's initial inflationary model, despite its elegance in addressing the horizon and flatness problems, faced significant scrutiny and debate within the scientific community. The graceful exit problem, as discussed, posed a serious challenge to the viability of the original scenario. Early reactions were characterized by a mixture of excitement and skepticism. While many recognized the theoretical potential of inflation, the lack of a comprehensive and consistent framework raised concerns. The paper sparked a flurry of research aimed at resolving the shortcomings and developing more robust inflationary models. Guth's work also ignited interest in the connection between cosmology and particle physics. Section 9. Subsequent developments and new inflation. The limitations of Guth's original model spurred the development of new inflation, pioneered by Andre Linde and independently by Andreas Albrecht and Paul Steinert. New inflation addressed the graceful exit problem by proposing a flatter inflaton potential, leading to a second-order phase transition and a smoother transition to the radiation-dominated era. This modification allowed for a more homogeneous reheating of the universe, Mitigating the problem of excessive density fluctuations, the new inflation model retained the core principles of Guth's original proposal while providing a more realistic and consistent framework. The central change was that the entire observable universe emerged from one bubble, eliminating the collision problem, Section 10, chaotic inflation, and eternal inflation. The concept of inflation continued to evolve, leading to the introduction of chaotic inflation by Andre Linde. This model proposed that the inflaton field could have a wide range of initial values, with inflation occurring in regions where the field was sufficiently large. Chaotic inflation eliminated the need for a specific phase transition, simplifying the inflationary dynamics. Furthermore, this led to the concept of eternal inflation, where some regions of the universe continue to inflate indefinitely, giving rise to a multiverse of bubble universes. This work expanded upon the idea of inflation to change our perspective on the very structure of space and time, Section 11 Observational Evidence and CMB anisocopies. The inflationary paradigm gained substantial support from observations of the cosmic microwave background CMB, precise measurements of the CMB anisotropies. By experiments such as COPE, WMAP, and Planck revealed a nearly scaling variant spectrum of density perturbations, consistent with inflationary predictions. The detection of the acoustic peaks in the CMB power spectrum provided further evidence for the inflationary scenario. These observations solidified inflation as a leading model for the early universe. The data aligned with inflation predictions to a degree that other models could not easily replicate. Section 12 Inflation and Quantum Gravity. Inflation presents intriguing connections to quantum gravity. Reconstructing the inflationary potential allows for exploring the physics at extremely high energy scales, potentially probing the realm of quantum gravity. The inflationary period may have amplified quantum gravitational effects, leaving observable signatures in the CMB or the distribution of primordial gravitational waves. The study of inflation provides a window into the early universe, but also into the fundamental laws of physics at the Planck scale. Many theories that seek to unify quantum mechanics with general relativity, such as string theory, also have to fit with the evidence for inflation. Section 13. Alternatives to inflation. Despite its successes, inflation is not without its critics, and alternative theories, cyclic models, such as the ekpyrotic scenario, propose that the universe undergoes repeated cycles of expansion and contraction, avoiding the need for an inflationary period altogether. Other alternatives include varying speed of light theories and modified gravity models. These alternative models seek to address the horizon and flatness problems through different mechanisms, challenging the dominance of the inflationary paradigm. Guth's theory remains the most popular, though due to its mathematical simplicity and explanatory power. Section 14. The multiverse and anthropic principle. The inflationary paradigm, particularly in the context of eternal inflation, leads to the concept of a multiverse. In this picture, our universe is just one bubble universe among an infinite number of others, each with potentially different physical laws and constants. This raises profound philosophical questions about the nature of reality and the role of the anthropic principle in determining the observed properties of our universe. Inflation has helped us examine the biggest of questions about existence. Section 15. Fine-tuning and the initial state. While inflation resolves the fine-tuning problems related to the horizon and flatness, some argue that it introduces a new fine-tuning problem related to the initial state of the inflaton field. The inflaton field must start in a specific configuration to initiate inflation and allow it to last long enough to explain the observed universe. Critics argue that this requirement constitutes a form of fine-tuning at the beginning of inflation. However, proponents of inflation contend that the initial conditions are less restrictive than those required by the standard Big Bang model. The trade-offs of fine-tuning present an ongoing point of discussion. Section 16. Bubble nucleation and the measure problem. In models involving bubble nucleation, such as the original inflationary scenario, The measure problem arises. This concerns the difficulty of assigning probabilities to different universes in the multiverse. The problem stems from the fact that the number of bubble universes is constantly increasing, making it challenging to define a meaningful measure. This problem has led to various proposals for how to calculate probabilities in the multiverse, each with its own set of assumptions and limitations. It's an issue that would need to be solved if the multiverse were considered a scientific theory. Section 17. The trans-Planckian problem. The trans-Planckian problem arises due to the extreme stretching of wavelengths during inflation, quantum fluctuations, that are observed in the cosmic microwave background today are wavelengths smaller than the Planck length in the very early universe. The problem stems from the unknown physics at the Planck scale, raising concerns about the validity of extrapolating known physics to such extreme conditions. It is a question of how certain we can be about physics at energy scales that we can never test. Section 18. Gravitational waves and B-mode polarization. Inflation predicts the generation of primordial gravitational waves, which would leave a unique imprint on the polarization of the CMB known as B-mode polarization. The detection of B-modes would provide strong evidence for inflation and allow for probing the energy scale of inflation. However, detecting B-modes is extremely challenging due to contamination from foreground sources and the weakness of the signal, which has proven difficult. Section 19. Future directions and tests of inflation. Future observations and experiments will continue to test the inflationary paradigm. Improved measurements of the CMB polarization, including the search for B-modes, will provide crucial insights into the early universe. Furthermore, studies of the distribution of galaxies and larger-scale structure can constrain the inflationary potential and the properties of the inflaton field. The search for primordial black holes represents another avenue for probing the inflationary epoch. Section 20. Inflation as a paradigm shift. Guth's inflationary model represents a profound paradigm shift in our understanding of the early universe. It provided elegant solutions to the horizon and flatness problems and offered a mechanism for generating the initial seeds of cosmic structure. Despite the challenges and ongoing debates, inflation has become a cornerstone of modern cosmology, influencing our understanding of the origin, evolution, and ultimate fate of the universe. It is not a question of whether the theory is right or wrong, but whether it can continue to evolve with new evidence. Section 21. Reflections on the original paper. Returning to Guth's original paper, one appreciates the clarity and courage to address fundamental issues, even in the face of unanswered questions. The paper's lasting contribution is less in its precise details, many of which have been superseded by subsequent model building, than in its conceptual framework, its identification of key problems, and the sheer audacity of proposing such a radical solution. Despite the initial incompleteness presented by the graceful exit problem, the inflationary universe served as a transformative catalyst for decades of research. The paper remains a shining example of theoretical physics being used to tackle observational questions about nature. Section 22. The enduring legacy of inflation. The enduring legacy of Guth's work extends beyond specific models or observational confirmations. It lies in the profound shift in perspective it engendered. By postulating an early period of exponential expansion, Guth revealed the universe as a dynamic, evolving entity with a history far more complex and surprising than previously imagined. This perspective has informed and inspired countless studies across cosmology, particle physics, and even philosophy. Its legacy lies equally in the questions it raised and the answers it spurred. In conclusion, Alan Guth's The Inflationary Universe, a possible solution to the horizon and flatness problems, constituted a groundbreaking contribution to cosmology. While the original model faced challenges, the core concepts of inflation have proven remarkably robust, finding increasing support from observational data. The paper skillfully addressed fundamental inconsistencies within the Big Bang theory, proposing a compelling solution that continues to shape our understanding of the early universe. Its enduring significance lies not only in its specific claims but also in its profound impact on the field, stimulating further research and transforming the way we view the cosmos. Despite evolving with new evidence and analysis over the decades, Alan Guth's foundational work remains a central pillar of modern cosmological thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.